In recirculating aquaculture systems, RAS, nitrogenous waste management is paramount for fish health and system sustainability. The primary waste product from fish is ammonia, NH3, NH4+, which is highly toxic. Through a process called nitrification, carried out by nitrifying bacteria in biofilters, ammonia is converted first to nitrite, NO2, and then to nitrate, NO3. While nitrate is significantly less toxic than ammonia or nitrite, its accumulation can still pose problems at high concentrations, leading to chronic stress, reduced growth, and environmental concerns if discharged. This is where denitrification systems come in. Denitrification is a biological process that converts nitrate, NO3, back into harmless nitrogen gas, N2, which then diffuses out of the water and into the atmosphere. This completes the nitrogen cycle within the RAS, allowing for significantly reduced water exchange and a more sustainable operation. How denitrification works. Denitrification is an anaerobic process, meaning it occurs in the absence of oxygen. It is carried out by a different group of bacteria called denitrifying bacteria. These bacteria use nitrate as a terminal electron acceptor in their respiration process when oxygen is unavailable. To do this, they also require a carbon source, electron donor. The overall process can be summarized as NO3 denitrifying bacteria, anoxic conditions, carbon source N2 gas plus H2O plus CO2. Types of denitrification systems in aquaculture. Denitrification systems in aquaculture are typically designed to create an anoxic environment and provide a suitable carbon source for denitrifying bacteria. Heterotrophic denitrification. Mechanism. This is the most common type. Denitrifying bacteria use an external organic carbon source, e.g., methanol, ethanol, acetic acid, sugar, proprietary organic compounds, as an electron donor. Types of reactors. Moving bed bioreactors, MBBRs. These reactors use plastic carriers, media, that move freely in the water, providing a large surface area for bacterial growth. Anoxic MBBRs are commonly used for denitrification, with a carbon source dosed into the system. Fixed bed reactors. Water flows through a stationary bed of media where bacteria attach and form biofilms. These can be upflow or downflow. Fluidized bed reactors. Similar to fixed beds, but the media is fluidized by the upward flow of water. Sulfur-based autotrophic denitrification, SAD. While primarily autotrophic, some systems use sulfur as the electron donor. Advantages. Can be highly efficient and predictable when managed correctly. Challenges. Requires precise dosing of the carbon source. Underdosing can lead to incomplete denitrification and nitrite accumulation, which is toxic, while overdosing can lead to excessive bacterial growth, increased biological oxygen demand, BOD, in the water, and potential hydrogen sulfide, H2S, production, also toxic. Requires careful monitoring. Autotrophic denitrification. Mechanism. Denitrifying bacteria use inorganic compounds, like elemental sulfur or hydrogen sulfide, as their electron donor and inorganic carbon, like bicarbonate, as their carbon source. Advantages. Does not require the addition of external organic carbon, reducing operational costs and the risk of organic pollution. Can also increase alkalinity. Challenges. Slower reaction rates than heterotrophic denitrification. Can sometimes produce undesirable byproducts like sulfate or elemental sulfur. And AMOX, anaerobic ammonia oxidation. Mechanism. A more recently discovered process, still under development for widespread aquaculture application, where specialized bacteria directly convert ammonia, NH4+, and nitrite in NO2 into nitrogen gas, N2, under anaerobic conditions without the need for an external carbon source. Advantages: highly efficient nitrogen removal, no external carbon source needed, Lower oxygen demand than nitrification, denitrification. Challenges: slow growth rate of Anammox bacteria, very specific and difficult to maintain operating conditions, temperature, pH, low DU levels, susceptible to inhibition by various compounds, requires advanced control. Integrated denitrification. Some RAS designs aim for single sludge systems, where both nitrification and denitrification occur within the same bioreactor, often by creating zones with varying oxygen levels. This can be achieved through intermittent aeration or by careful hydraulic design. Biofloc technology, BFT. While not a dedicated denitrification system, BFT inherently promotes denitrification in the anaerobic zones within the biofloc particles and the pond sediment, contributing to overall nitrogen removal. Benefits of denitrification systems in aquaculture. Reduced water exchange, the most significant benefit. By removing nitrate, the need for frequent water changes is drastically reduced, conserving water resources, minimizing effluent discharge, and saving on heating and cooling costs for the culture water. Improved water quality. Prevents the accumulation of nitrate to toxic levels, contributing to a more stable and healthy environment for aquatic animals. Enhanced biosecurity. Reduced water exchange means less introduction of pathogens from external water sources. Alkalinity recovery. Heterotrophic denitrification consumes acidity produced during nitrification, helping to stabilize pH by regenerating alkalinity. Sustainable aquaculture contributes to a more environmentally friendly operation by minimizing nutrient discharge into surrounding water bodies, addressing regulatory concerns regarding aquaculture effluent. Higher stocking densities. Cleaner, more stable water allows for greater biomass per unit volume, increasing productivity. Cost-effectiveness. The initial investment for denitrification systems and the ongoing cost of carbon sources for heterotrophic systems or specialized media can be significant. Local availability and pricing of these inputs will be crucial. Technical expertise. Operating and monitoring denitrification systems effectively requires a good understanding of microbiology and water chemistry. Training for local farmers and technicians will be essential. System complexity. Denitrification adds another layer of complexity to RAS. Simpler, robust designs might be preferred for widespread adoption in Bangladesh. Energy requirements. While reducing water exchange saves energy on pumping, some denitrification systems still require power for pumps, mixing, and monitoring equipment. Carbon source availability. For heterotrophic systems, ensuring a consistent and affordable supply of a suitable carbon source is vital. Locally available organic waste streams, e.g. molasses, fermented agricultural byproducts, could be explored as cost-effective alternatives. Integration with existing practices. How easily can denitrification systems be integrated into common aquaculture practices in Bangladesh, e.g., pond-based systems, smaller-scale RAS? Research into decentralized or modular solutions might be beneficial. Thank you for watching.